May 2021. Inspectors found a massive crack hidden deep within the bridge built in 1973 that carries over 50,000 vehicles a day across the Mississippi, one fracture in a single non-redundant beam. If that piece had failed, the entire Hernando de Soto Bridge could have collapsed, closing a critical artery of American freight overnight. But here is the alarming part. Across the U.S., more than 7,500 bridges are classified as structurally deficient. The nation's overall infrastructure just earned a C- grade, and repair funds remain slow even after billion-dollar legislation. So how did America's most indispensable bridge come inches from disaster? And what does it reveal about the fragile state of everything we depend on? When the Hernando de Soto Bridge first opened in 1973, it represented the promise of modern engineering, a sweeping steel arch stretching nearly 2 miles across the Mississippi River. The design was ambitious for its time, built to carry the relentless flow of interstate traffic between Memphis, Tennessee, and West Memphis, Arkansas. Over the decades, the bridge became a fixture of daily life and commerce in the region, quietly absorbing the weight of more than 50,000 vehicles every single day. That number is not just a statistic. It means thousands of commuters, families, and truck drivers depending on this crossing to get to work, deliver goods, and keep shelves stocked across the country. Roughly 30% of that traffic is heavy trucks, hauling everything from grain and steel to electronics and medical supplies. The bridge is a key link in a supply chain that stretches from the Gulf Coast to the Midwest and beyond. Every hour, an unbroken stream of 18-wheelers and passenger cars rumbles across its 6 lanes, feeding the economic engine of Memphis, a city whose port handles more than $9 billion in goods each year. The Interstate 40 corridor itself is valued at over $400 billion in annual freight, and for many shippers, there is simply no practical alternative. Behind the scenes, the Tennessee Department of Transportation, called TDOT, acts as the bridge's caretaker. Their teams are responsible for regular inspections, maintenance, and emergency response if anything goes wrong. The stakes are enormous. A single closure can disrupt regional commerce, strand travelers, and trigger costly detours for tens of thousands of people. For TDOT and its partners, the challenge is constant vigilance, because the bridge is not just a local crossing, but a critical artery in the nation's infrastructure. Its daily burden is a reminder that even the most impressive structures are only as strong as their weakest point. The Hernando de Soto Bridge was designed as a tied arch structure, a type of bridge where the arch's outward forces are held in check by a long steel member running beneath the roadway. In this case, that member is called the tension tie. According to federal standards, it is classified as a fracture critical member, abbreviated FCM. That means if it fails, there is nothing else to hold the bridge together. There is no backup. The entire span depends on the integrity of this single steel box, welded from thick plates and running the length of the arch. Forensic engineers from Wyss, Janney, Elsner Associates, the team called in after the 2021 closure, described the risk in blunt terms. A complete break in the tension tie could have caused a partial or total collapse of the bridge. The fracture that was discovered was not just a surface crack. It ran through the outboard side plate, the top cover plate, and into the bottom plate, evidence of a failure that had started years earlier, likely at a weld repair site, and then progressed unseen. Their metallurgical analysis pointed to hydrogen embrittlement as the culprit, a tiny flaw at the weld that, under decades of stress from traffic, grew into a critical crack. Unlike some bridge designs, the tied arch at Memphis offers no redundancy. If the tension tie is severed, the arch cannot transfer its load, and the span could fall. This is what federal highway engineers mean when they use the term fracture critical. There is no second chance. That is why after the crack was found, inspectors used ultrasonic testing, sending sound waves through the steel to check for hidden defects. It is a technique that can spot flaws deep inside a member, even when nothing is visible from the outside. The forensic findings made clear, the bridge's safety rested on a single, non-redundant piece of steel, and the margin for error was razor thin. Freight operators remember the day the bridge closed as a turning point. With Interstate 40 suddenly off limits, every truck headed across the Mississippi was forced onto the old Interstate 55 bridge 5 miles south. That detour might sound minor on a map, but for drivers hauling perishable goods or just-in-time shipments, it meant hours lost in crawling traffic. Each extra mile burned more fuel and pushed delivery schedules into chaos. According to Tennessee Department of Transportation data, the rerouting added about 5 miles per trip, and for nearly 30,000 trucks a day, that translated to over $13 million a week in extra fuel costs alone. Local manufacturers, surveyed by the Memphis Chamber of Commerce, reported losing an average of $45,000 a day as shipments stacked up in warehouses and supply chains seized. One logistics manager described the scramble: trucks idling for hours, drivers on the phone with dispatch, customers calling for updates no one could give. At the same time, Tennessee Department of Transportation crews worked around the clock. Engineers, welders, and inspectors were on rotating shifts, floodlights blazing through the night. Temporary steel plates were bolted over the fracture to stabilize the tension tie, while fabrication shops raced to build permanent splice plates. Every hour counted, not just for the bridge, but for the thousands of people and billions of dollars moving through Memphis each day. The disruption rippled far beyond the city. Grocery stores in Missouri waited on delayed produce. Auto plants in Kentucky adjusted assembly lines. From the outside, it was just a closed bridge. On the ground, it was a test of how much strain a single point of failure could put on an entire region. For everyone who depends on that river crossing, the lesson was clear. When the margin for error is razor thin, the consequences aren't just technical, they're personal and they're costly. Across the United States, the Hernando de Soto Bridge is far from an outlier. According to the National Bridge Inventory, more than 7,500 bridges nationwide are classified as structurally deficient. That means they carry heavy traffic each day despite having at least one key element, like a deck, superstructure, or support, rated in poor condition. Many of these bridges form vital links in the country's freight network, handling trucks, commuters, and emergency vehicles with little margin for error. The Memphis Crossing is just one piece of a much larger puzzle, where aging steel and concrete are stretched to their limits by decades of use and millions of load cycles. The American Society of Civil Engineers grades the nation's bridges at a C and the overall infrastructure at a C-. That is not a passing mark, it is a warning. Even though the number of deficient bridges has fallen slowly over the past decade, progress is outpaced by the sheer scale of the backlog. Many of the most vulnerable structures are fracture critical, like the Memphis Bridge, meaning a single failure could have consequences far beyond the local area. The Hernando de Soto Bridge is just one example, but its story is echoed in thousands of river crossings, highway overpasses, and urban viaducts from coast to coast. The numbers do not just reflect aging infrastructure, they reveal a national challenge that demands attention, resources, and a willingness to confront uncomfortable risks. Congress passed the Infrastructure Investment and Jobs Act with the promise of transforming America's aging bridges. The law set aside $27 billion specifically for bridge repair, a figure that dwarfs previous federal efforts. But the money has not brought quick fixes. According to the Federal Highway Administration, only about half of the authorized funds had reached actual projects by 2024. The rest sits in a kind of bureaucratic limbo, caught up in layers of approvals and matching requirements. States are required to provide a share of the funding, often 20% or more, before they can access federal grants. For cash-strapped transportation departments, especially in rural or lower revenue states, coming up with that match can delay projects for years. Even when money is technically available, it does not flow straight to the bridges most at risk. Each grant application must pass through a maze of federal guidelines, environmental reviews, and competitive scoring. The process can stretch for months into years before construction even begins. A policy analyst at the Eno Center for Transportation described the system as a pipeline clogged with paperwork. He pointed out that while Congress celebrates big numbers, the reality on the ground is far slower. We have the money on the books, but the bridges are not getting fixed. The result is a backlog that grows even as new funding arrives. The Hernando de Soto Bridge, for example, received partial funding through the FAST grant stream, but a significant portion of its repair budget is still waiting for final approval. Across the country, thousands of bridges remain stuck in the same slow-moving queue, highlighting the gap between legislative ambition and the hard realities of public works. Beneath the sprawling streets and towers of Mexico City lies the soft, shifting memory of a vanished lake. This is the basin of ancient Lake Texcoco, a vast depression once filled with water and now packed with thick layers of clay and silt left behind by centuries of sedimentation. These lakebed deposits, sometimes reaching depths of 15 to 30 meters, are not the solid ground most cities rely on. Instead, they are made up of fine-grained particles and a high proportion of empty space, or voids, between them. This unique structure means the ground is naturally prone to compression. Even before modern development, the weight of overlying sediments and the slow escape of water from these clays caused the ground to settle, sinking by several centimeters each year. UNAM geotechnical researchers have spent decades mapping the mechanics of this slow-motion descent. Their studies show that the process begins at the microscopic level. As water drains from the clay, the particles rearrange and pack closer together, causing the land above to drop. This compaction is especially intense in the former lakebed, where the soils are still saturated and loosely packed. Unlike the stable bedrock found beneath many world capitals, Mexico City's foundation is more like a sponge, one that compresses under pressure and never fully springs back. Over the past century, this natural tendency has led to a staggering cumulative effect. By combining historical leveling surveys with modern satellite data, scientists have documented total subsidence of 9 to 10 meters across wide areas of the city. That is enough to swallow a 3-story building, and it is not an isolated event. The entire urban core, from the Zocalo to the outer districts, has slowly but relentlessly sunk closer to the old lakebed floor. While the ground would have settled to some extent even without human interference, the city's geology has set the stage for a much larger crisis, one that will be driven not just by nature, but by the choices people make above and below the surface. Every day, Mexico City's water system pumps more than 4 billion cubic meters from the aquifer buried beneath the old lakebed. This relentless withdrawal is the city's main source of water, and its greatest threat. As pumps draw down the groundwater, the soft clays of the former Lake Texcoco compress, causing the ground above to sink. In some districts, the pace is staggering. NASA's Jet Propulsion Laboratory, using satellite INSAR radar, has tracked hotspots where the city drops by as much as 50 centimeters each year. These are not isolated pockets. Entire neighborhoods, home to millions, are caught in a slow-motion collapse. The consequences reach deep into the city's infrastructure. Water pipes, many laid more than 70 years ago, are now warped and broken by the shifting ground. SACMEX, the municipal water authority, estimates that 40% of all water pumped into the system never reaches a tap. It leaks away through thousands of cracks, feeding the very subsidence that created the problem in the first place. The city loses nearly 2 million cubic meters a day, enough to supply a medium-sized metropolis, while residents in outlying boroughs line up for water trucks. The damage is visible above ground too. The Palace of Fine Arts, a national icon, has tilted and sunk more than 4 meters since it opened. The Metropolitan Cathedral, once the tallest structure in the city, now leans at a visible angle. Engineers tasked with preserving these landmarks have documented new cracks and foundation shifts every year. Peer-reviewed studies from UNAM and NASA's Jet Propulsion Laboratory confirm that the city's core, from the Zocalo to Iztapalapa, is sinking at a pace unmatched by any major city on Earth. For the 22 million people who call Mexico City home, this is not a distant threat. It's a daily reality, measured in centimeters, broken pipes, and the slow tilting of history itself. No single intervention can halt the sinking of Mexico City, but scientists and engineers have assembled a menu of practical options. Managed aquifer recharge stands out among the most promising. In pilot projects led by UNAM and Conagua, treated wastewater is injected back into the aquifer beneath the city. Early results show that in some peripheral districts, the ground has even rebounded by up to 2 centimeters per year after extraction rates dropped. Yet these gains are fragile. High costs, complex geology, and the risk of contamination in clay-rich layers make large-scale recharge a slow, expensive prospect. Pipe repair and replacement offer more immediate relief. SACMEX, the city's water authority, has invested hundreds of millions of pesos in replacing leaky lines, aiming to recover flows lost from the Cutzamala system. In 2024 alone, 46 separate works target the worst leaks, building on earlier pilots that stabilized metro stations like Acatitla. Even so, the scale is daunting. About 40% of piped water still escapes through cracks, and the backlog grows as new breaks appear faster than crews can fix them. Regulating groundwater extraction is another essential step. UNAM researchers have called for strict caps and pricing reforms to rein in the city's dependence on wells, which still supply about 60% of all water. But political resistance is fierce, and enforcement remains patchy. Some progress is visible in satellite data. NASA's INSAR maps show that districts with reduced pumping have slowed their descent, but deep compaction continues in the historic core. For landmarks at risk, engineers have turned to targeted underpinning and micropiles. The Palace of Fine Arts and sections of the metro have received these reinforcements, buying time but not solving the root problem. Expanded satellite monitoring now guides these efforts, with real-time INSAR data helping authorities spot new hotspots before cracks appear at street level. No solution is quick or easy. The city faces trade-offs between cost, disruption, and the sheer scale of intervention needed. Experts from UNAM and NASA agree the best path forward is a layered approach, combining recharge, leak reduction, smarter regulation, and constant monitoring. Even then, the city will likely keep sinking, just more slowly. The hard truth is that adaptation, not reversal, is the most realistic outcome for the next generation. Right now, over 7,500 US bridges are classified as structurally deficient. The Hernando de Soto Bridge, built in 1973 and carrying more than 50,000 vehicles a day, narrowly avoided becoming a headline tragedy. Even with the infrastructure bill, repairs lag behind the risk. The American Society of Civil Engineers still gives the nation's backbone a C-. Until we act, our luck is the only thing preventing catastrophe. What's holding up your daily world? Let me know below.